everyone, welcome back to our YouTube channel Becoming a ROS Developer. I'm Desire, and today we've got Oliver who has just completed the course Gazebo Sim Basics. So he'll be giving us a presentation on that. So first of all, we'll begin by seeing how we managed to get the real robot dimensions first, and I'll let him do the rest of it. So without further ado, let me hand over the platform to him.
Yeah.
Alright, Oliver, whenever you're ready.
Yeah, well, thank you very much. Yeah, I'm Oliver, and I will show my results on the Gazebo simulator course. I hope you can all see the screen. So on the top here, we have the real robot lab, which is called the small city lab. We have this turtlebot robot in this kind of street scenario. And what we can do here is we can already, just by starting the robot streaming, move the robot around with this interface here, like moving back, turning, and so on. Now, the goal of the project was to recreate this whole scene and the robot with the Gazebo simulator. And for that, of course, first we need a robot description file, like a description of the robot, how it looks and how it's actually set up. And to show that this is not existing first, I want to quickly check the published topics currently. So there are a few topics published, like for example, this command velocity we use for actually commanding the robot to move. We have the joint states of the robot, so that is all the things that the robot is already publishing and providing to us. But you cannot see any robot description yet. So let me check here, there is no robot description we can use. Now I will make a like a brief leap. So let me quickly get something started. So now I will start the ROS, so the visualization, and you can see we have a model of our robot in here. So you already provided all the meshes, so basically the, let's say the way how the robot looks, the wheels and the body, but of course we have to find out how it's actually put together. So we only have the single parts, but we have to put them together in a specific way so that it really resembles the real robot. And also we have to connect the model with the real robot, so with the robot joints and what parts are moving and what not. So just quickly checking how it looks if I'm moving around from the top here. You can see that also the model in ROS is moving around, like turning and moving forward and backward. So this is not all. The robot also has a LiDAR sensor, or LiDAR scanner. I just quickly have to change the topic here we are looking in, and then also we see the actual information published by the robot LiDAR scanner. Yes. So that when we are moving around, we can also see that this is updated depending on the position of the robot and where it is looking, so to say. Of course, the LiDAR is 360 degrees, but still, if you're moving the robot, there of course are some uncertainties that will make it move a bit.
Right.
Okay, but still, I didn't explain how I actually got all those information and how I put everything together. And there are a few ways this can be done. You can also later share on the slides. So first thing we need to know is we have to find out which frames are being used by the robot. So for example, the wheel frame, or like all the frames that are on the side here, the base part, of course, the base link, then also where the wheels are, and the LiDAR scanner where it is positioned.
Yes.
And in order to do so, we can use like a command line tool that is called like from the TF2 ROS package, the TF2 Echo. To use that, when we just quickly do the help part, you can see that we need to give it a source frame and a target frame.
Right.
And we can actually do the echo rate. But so in order to get the transformation from one frame to the other, we have to provide both frame names, and then we can get the actual transform. Still, we don't know which frames we are looking into in the very beginning. Okay. And in order to find that out, we can use another tool, which is from the TF2 tools package. Tools. And then it's called the view frames. And the view frames is basically recording all the transform data that is published, and then saving it in a PDF file and providing kind of a tree. So if we quickly go into our files here and open it, then this is the PDF file, and you can see the whole kind of frames and the transforms from which frame to which, so to say. So it's not the actual transform information, like how it is transformed, but just how it's connected. So we start with the odometry, go to the base footprint, the base link, and then from the base link of the robot, we can go to all the caster backlink, the caster wheel. We have the base scan, so the kind of position of the scanner, the wheels, and also the IMU.
Yes.
So with that, we have the names. And then when we just take, for example, the base link and now one of the wheels, like the wheel right link, can just use the tool I mentioned before, the TF2 echo. We can say base link, and then it was, now I have to double check how it was called, wheel left link, for example.
Yeah.
And then it will always give the transform information that is published. So it runs through with the times, of course. I will quickly stop, then we can have a look. So for example, at this specific point in time, it was transformed from base link to the wheel left link with that translation. So we have those X, Y, Z coordinates, or like the transformation, and then also the rotation in those different ways. Though, for example, the rotation with the wheels, especially since the wheels are moving and rotating, of course, this will always change depending on how we are like using the robot. So, for example, right now, since the robot was standing still, those were pretty much similar, or the same. But if I would move the robot now, this would change. But still, the translation would stay the same because we are not moving the wheel from the base of the robot away, but it will always stay in the same position.
Yes.
Okay, so this is, let's say, the first step. So in order to get this kind of robot model here in Harvest properly aligned, also with the scanner and just those different parts. So maybe quickly put those away to see it better. Having the LiDAR scanner on the top, having the wheels on the bottom part here, also on the other side in the base, the robot. So now this is the robot. It's nice. We have this kind of visualization of the robot, but still, of course, there is a bit more to recreate this whole lab in a simulation. And for that, I would actually now continue quickly with a few slides and then show the whole simulation, just explaining how I created the simulation and then come back to the actual simulation.
Sure.
Change the sharing, or can I do it like this? I don't think so, right? Can you see the slides?
Not yet.
Okay, then I have to quickly change this one here. Okay. So
okay, now we can see them.
Okay, perfect. So this is the part I more or less explained already. So in order to create the URDF file, so this robot description file, or also the Xacro file if you want to use some additional functionality. I mentioned the measures were provided by you and the frame information we can get with it. There are actually different command line tools you can use from ROS2. You could also just go and echo the whole transform topic and then find out which frame to which frame was transformed in which way. So there are different ways. I just decided to use this one. As you can see here also the tree, the few frames tree, and then in the top here the ROS2 TF2 echo command. Now, okay, one thing I forgot actually. So in order to recreate the map in our simulation, we need information like how big it is and how far it reaches. And in order to do so, I already showed you also the laser scan functionality of the robot. In order to do so, I positioned the robot in a specific way so that we can see all four walls of this kind of table setup. And recorded the laser scan values of that robot by just, as I also put in here, using the topic echo of the topic scan. So scan is basically providing all the laser scan information. And since it's a 360 degrees scanner with 720 like values, you can relatively easy decide which ones you have to use. Of course, in order to do so, you have to position the robot in a specific way, like parallel to the wall, so that you can easily say, okay, this is front, back, left, and right.
Right.
Also, alternatively, I think I didn't do it, but you theoretically could also move the robot from one end to the other and just see by the position information how far it was going or how the position changed, so that you can kind of calculate what the size of the area is. But I
Okay.
think with a laser scanner, it's relatively easy.
Right. Yeah. I would think so too. Yep. Because you don't have to move it around as much.
Exactly,
Yeah.
exactly. Okay, then to actually recreate the whole lab, we need models and plugins. So first, of course, we need models of all those different things that are existing in the laboratory, but also the whole table itself. So start with a kind of empty world, and we put everything together. For example, the table, the different objects, like on the right side, this traffic sign, the background, but also the ground itself. So there is a lot you have to put into the simulation to really recreate it. Those models have two necessary parts. First, it's the model SDF, so this kind of description file for the model, kind of similar to the robot description file, but just in this case for the simulation, and the config file, which gives a bit more meta information. Then what you can do is provide meshes for example, pictures. Like on the right side here, this arrow, of course, you have to provide this picture information in order to display it. And then also there is a specific thing we used, which is the actors. So basically simulated actors, or like living things that are moving around. And for those, you first need the information about the animation, but also the movement paths you have to decide or define. So both things have to be put in, and I can also later share a bit in the file system how this looks. There's one thing you provided, which is the .dae file. So basically some scripts how to properly incorporate those meshes and pictures. So this is something you have to also consider, how to actually include them. It's not just like putting it in, but there is a bit more to it. But this was provided by you. Now, even if we now have all those objects and the world is filled with those things in the simulation, in order to use our robot in that simulation the same way we use the real robot, we still need additional things like which is called the plugins. We need it for communication, but also for simulation of the robot. And I kind of differentiate here between two types, so to say, or the plugins I used in the world file and also in the robot file, which is a bit different. So for the world, I put in here, for example, the physics plugin. Of course, we want some gravity. We want that the objects, if you are running into them, are like properly reacting to it as we would expect from reality. We still also want to be able to do the user commands in the simulation. There is the scene broadcaster. We also now, the two special things, want the sensors in the world. So we want to say that in our world, we have sensors that will also be kind of giving information to the outside. Like the first thing is the sensors more specifically for the laser scanners, but also then for the IMU. And for the robot side, in order to properly use the robot, we first need this differential drive plugin. So because we have a robot with two wheels left and right that are basically taking care of the actuation. This is a differential drive, and in order to move our simulated robot, we have to have this plugin defined with all the information, which wheels, how far are they away from each other, and so on, to properly calculate the dynamics of the robot. Also, we need the joint state publisher. So this is, as you saw, the wheels of the real robot were also moving in the visualization of ARVIS. And this is because we always have this joint state publisher, which is publishing the joint information of the robot. So whenever like something is moving, for example, the wheel, the joint is also, of course, rotating, and these information have to be provided to the system, to ROS. And therefore, we need this joint state publisher in our simulated robot to also have those information outside of the simulation.
Yes.
And additionally, I put in here the sensor and IMU definition. So to say, the counterpart to the plugins of the world, we of course need to define the sensors and the IMU we are using in the robot, so that these parts are working together, so to say. So the sensor is working on the robot, but in the world file, we have the plugin that is basically providing the information then to the outside.
Right.
So the whole system would kind of look like this. We have the Gazebo simulation on the left side with our world file that includes all the models, the actors, and the plugins. While, of course, the models are, let's say, their own packages where we have the config and SDF files, but also the meshes and image files and so on. And for the robot, we have our robot description where we have the different links and joints defined, but also, as I mentioned, the different plugins that we are using. Now, in order to also use our ARVIS and the tail operation interface, there is different ways of ROS2, we have to connect the Gazebo simulation with ROS2. And this we do with this Gazebo bridge, where basically the Gazebo topics and the ROS topics are connected to each other.
Mm-hmm.
In a way that we decide how. So there is a way to only bring Gazebo topics to the ROS2 system, but there's also the other way around, or basically both to each other, so to say. So we are, for example, connecting for example, the robot, the joint state publisher of our robot is publishing the information in the Gazebo simulation. So we have a topic in the Gazebo, but we want to have it also in ROS2 in order to visualize properly the joints in ARVIS. So there we have the connection from the joint states of the Gazebo with our bridge that is providing this information to the ROS2 system. Okay, and with that, I think that's enough. Now I would actually go into the simulation.
Yes.
To actually see something and how it looks. So. Okay, now we are still at the real robot here. I will turn that off now. And also I will turn off ARVIS here. Oh, there was an error. And I'm thinking now, actually one of the major difficulties I had was the performance of the simulation. So I actually had to fiddle around in order to get it running kind of properly and stable, but it might be a bit laggy, so just bear with me.
Okay.
I would actually do it in two ways. So first I would just start with the world without the robot, and later I would start the whole thing with the robot.
Okay,
just to have a look for how the world looks.
Yeah, just checking our time. So you've got plus or minus 5 minutes. So.
Okay, I will go through quickly.
All right.
maybe I will do it like this. It's okay.
Yeah. Well, would rather see it than not see it. So yes, give it your best shot.
Maybe I will. No. Okay, I will stop this. I will stop it again. I will just directly go into the main part with the robot. So. And you can now it's a bit difficult, but you can see here creating the GZ ROS bridge, for example. You can see in the command line here. Okay, it starts. Oh, there are quite a number of warnings now. So, okay, there it is. Okay, put this away. It's a bit annoying. Okay, so this is our world. I don't think it's. I'm not sure now, but I'm not sure if you really have the mountains in the background like that. But either way, this is what you provided at the background. We have these mountains, we have some grass, and also like asphalt here where our table is put on.
Yes.
And I will scroll into a bit. There is one person walking around very slowly. That's because we are only running with 10% real-time factor. So basically 1 second means 10 seconds in simulation. And this is what I mean. I really struggled to get it running like performant with all the objects. But either way, I can show the functionality. Are you still here?
Yep, I think I lost you a bit. So
okay.
Just 1 sec. Can you zoom into the sim world a little bit more?
Do it like this for now.
Yep. Okay, so we can see the robot.
Okay, yeah, we have the table here. We have this kind of tracks for the robot, as you saw of the real robot. We have the objects, the different traffic signs, and also this kind of wall you put into there. And we have our robot here. And now, if we want to, if I can show you, we can also visualize our LiDAR scanner in the Gazebo simulator. So, just add this part here, and then we need to quickly change the topic, and then it will also show the scanner. It should, yes. And what you can see is that basically some of the rays are being blocked by the different objects, which basically mean that it's working perfectly fine, because this is what you want to have. So the LiDAR scanner is actually of the objects are working fine.
Mm-hmm.
And it's kind of like the signs are at the same height as the robot scanner, so that's why it's hitting the signs and not the small bars, so to say.
Okay.
Now I will quickly like this. I will go a bit closer even, but I will turn off the LiDAR so that we see a bit more, and I will make it a bit smaller. But what we can do now, just to show that it's connected to the and we can move the robot in there, and in parallel I will try to put it on the bottom here, just to see also the harvest, where the robot then also will move around. This. Maybe quickly check why the LiDAR is not showing. Should be this one. Is it scan? Oh, it's scan. Sorry. Okay, now we can also see like the LiDAR scanner in Abyss, and if I move around with the robot, now also in Abyss it's moving around. Oh, is it? Something's up here with the walls. Okay, wait, there is a... Okay, Abyss is not working properly right now. It should stay there, but actually it should move around.
Yeah.
It's strange now, but okay, let me first concentrate on the robot. So it's moving basically means that the teleoperation interface of ROS2 was working together with Gazebo.
Yeah. It's moving in the sim, but it's just the RFS that's not updating quickly enough, I guess.
I'm not sure. It looks like it's standing still, but I have to double check why it's doing that right now. But it actually moves. It's just the LiDAR scanner's not.
Oh, that's not moving.
Probably it's taking the one of the real robot right now. Probably that's why.
Oh, try
because
disconnecting.
Streaming.
Yeah, try disconnecting and then let's try again. Oh.
So it was probably kind of overwriting the scan topic.
Yeah. So I think running it now without the robot connection, then we can be able to actually see the laser scan data change.
Okay. I will just quickly start it again, and then can have a look for others. But yeah, I think that was mostly it what I wanted to show. So just quickly restart. This. Operation. Oh yeah, now it's also properly positioning.
Okay.
In Arvis as well. I will quickly go here. Bigger. And now do this one again. Yes, it's good. And now moving again. And now it's moving in Arvis and in Gazebo.
Right. Brilliant.
That looks better.
Yeah, much better. Thank you. That's good. All right. So I think since we've just seen this wonderful presentation, I will now get into the questions.
Yes.
Okay. So first thing, right? I'd like you to take us through the whole process of matching topics, right? Via the Gazebo bridge, right? What challenges did you experience? Because there are some subtleties there between ROS topics and the Gazebo topics. So can you explain that process a little bit more? Yes, how did you do it? Did you have to do any type of namespace matching or remapping of topics?
Yes, so there was actually when I mentioned the difficulty of the performance of Gazebo, the second, let's say, major difficulty I had was the laser scan data, which was, as you mentioned, just because of, or more or less, not exactly the namespace, but more of the frame. So when, let me quickly go into the files here. So if we go to the robot Xacro file, I have the laser scanner down here, where it says we have the Gazebo reference, so the base scan, which is the frame. Then it says the sensor type and the name, this head Hokuyu sensor.
Yes.
And what I didn't do is I didn't define this Gazebo frame ID. So when this was missing, it was basically still providing the topic laser scan, but the frame was a kind of concatenated thing of base scan and the head Hokuyu sensor and so on. And while I was able to bridge the laser scan topic of Gazebo with or to the scan topic of ROS2, it wouldn't fit the frame because it was not the base scan frame, but it was this kind of concatenated frame.
A combination, right?
And I really struggled to find out what was going on because I checked like the bridge, if it's working, if I maybe did a problem there. I checked the Gazebo topic, which I mean you can do easily, more or less similar to the ROS2 part, where you can just echo the topics. You can also say Gazebo topic, for example, and then we say -L for the list, and then you get the list of the Gazebo topics, and you can also here see the world and new world, which is basically my world, so I call it new world, and where you have some of the information, but you also have then the laser scan. And this basically is the one I wanted to communicate to ROS2 with my bridge. But yeah, I had difficulties with the frame, and this was giving me a lot of errors in ARVIS later, even though the information were received from the ROS2 side. But yeah, then I found that I had to define this Gazebo frame ID so that it does not take the reference base scan and the head Hokuyu sensor as a concatenated thing, but just takes the base scan as a frame. And then it was working fine. So this was more for the frame part. It was not about the topics specifically, but of course frames. In these plugins here, you decide which topics is also being published. For example, here down there in the IMU, it also says that you use the topic IMU, for example. And then as you can see here, we have also the IMU topic in Gazebo.
All right.
Yeah, I don't know if this answered your question. It was a bit more about the frames, but
it does, because there's also differences between. There might be differences between the robot and the way the frames are mapped to Gazebo. So yeah, I understand. All right. The next one that I want to ask is with regards to the joint state publisher, right? So you do have to use the joint state publisher when you are running the real robot, right? Why is it that you don't have to use it when you are using simulation, for example?
Oh, now I'm a bit confused. So when I'm using the real robot, basically the robot is providing the joint states, right? So there is a joint state publisher, I'm not sure running in your system, but it's providing already the joint state topic. For the simulation, I have to do it myself or start it, so that's why I have this joint state publisher plugin here, where it also has the joint states topic. And when looking into my bridge, I also have the joint states here being bridged from the Gazebo part. So this is the direction. Oh no, I changed it. Oops.
Yeah.
From Gazebo to the ROS2.
Yeah.
And I have to do it so that so I need the joint states in order to properly visualize, right? So if I don't, yes, exactly. If I don't have the joint states, my wheels in the bottom here, they would kind of be lost. They wouldn't know in which state they are, because with the robot description, I only once, so to say, get the information of my Xacro file, how the robot is set up generally, but I don't get the dynamic information when it's moving around.
Yes, true.
So for the joints that are not fixed, but for example, they rotate continuously or so, like the wheels, then I need these joint states to actually display it in ARVIS as well.
Yes, that's correct. You actually corrected the way I asked my question. So yeah, thank you very much.
Okay,
that's
exactly
how
I
it
understood
works.
correctly. Okay.
That's exactly how it works. Yes, you don't need it for the real robot, but you need it for simulation. So yeah, that's cool.
Yes.
The last question is concerning the use of plugins, right? There's a difference between Gazebo Sim and Classic, right? Can you explain to me why do we need plugins in our world files versus what used to be done with Classic, where you could just have Gazebo plugins in the robot description file rather than the world file?
Okay, yeah. So I'll be totally honest. I'm not exactly sure what the answer is to that.
It's all good. It's just general.
My assumption is that for the robot part, I mean, we have the plugins that are directly connected to the robot. For example, the differential drive needs information of how the robot is set up, like the joints, like how the wheels are separated and so on.
Yeah, yeah, yeah.
But for the world, we want to, in the world, we want to have these plugins to actually give it to the outside, meaning that we can actually connect those information with ROS2.
Mm-hmm. It's
Um,
actually for the differential drive and the, what's the next one? Differential drive and
joint status here?
yes, those ones, they are fine in the robot description file. They're actually supposed to be there. It's just the other ones for the sensors that need to be in the world files. And so mostly,
Okay, those two.
yeah, the reason why we actually have sensor plugins in the world files is actually because that's where the physics actually is happening, right? Whereas with classic,
True.
this needed not to be done exactly. There was no strict rule that said we should have them there.
Okay.
So it works better in simulation in the word files, because then you don't have your simulations dependent on the robot itself. So you just have the
Yes.
sensors
Yes.
in the word files, and when you change a robot, you don't have to go and actually change the sensor itself if it's the same sensor. So yeah.
Okay, true, true. So theoretically, I could just put in a sensor in my simulation world and use it without having the robot like that. But just
Yeah,
because I already have a plugin in my world file, then everything is already prepared.
yeah, that's correct. That's correct. All right. Thank you very much for your wonderful presentation, Oliver. It was very nice and very educating, both to
Thank you.
me who is watching and everyone else who is watching as well. It's very important to at least talk about these things as we get to find and probe our understanding of these concepts. So, all right. Wonderful. Congratulations to you. All right, everyone. This was Oliver's presentation, and would like to congratulate him. A warm congratulations to him, and would like to encourage all those of you who would like to try this course and come and showcase their work to do so. And until then, keep pushing your ROS learning. Bye bye.